Okay, good morning. Let's get going. So, as always, I'll start with the review. And today, we embark on another major milestone in our analysis of lumped circuits. And it's called the sinusoidal steady state. And again, I believe this will be the second and the last lecture for which I will be using view graphs. And the idea here is that just like in the last lecture, there is a bunch of mathematical grunts that needs to be gone through. And I'm going to show you a sequence in a little chart today that talks about the effort level in doing some problems based on time domain differential equations as in the last lecture. Something slightly different today and something much better on Thursday. And so in some sense, Thursday's lecture and today's lecture involve talking about the foundations of the behavior of certain types of circuits. And it's good for you to have this foundation as background. But when you actually go to solve circuits, you don't quite use these methods. You use much easier techniques, which I will talk about next Thursday. So let's start with the quick review, and then we'll go into sinusoidal steady state. So the last lecture, we talked about this circuit, and so did we. And we did the same 2 lectures ago on Tuesday. So we had one inverter driving another inverter, and we said that the wire over ground has some inductance. CGS is the capacitor of the gate, and R is the resistance at the drain of the first inverter. And if you look at the circuit, that circuit formed an RLC pattern. And what we did was we said, let's drive this with a 1 to 0 transition at the input. And the 1 to 0 transition at the input would cause this transistor to switch off. And this node would then go from a very low value to a high value. So it is as if a 5-volt step was applied at this input. We also saw that using time domain differential equations, that by applying a step input here, the output looked like this. The output would show some oscillatory behavior when we have a capacitor and inductor. I also gave you some insight as to why it oscillates like this. And you also heard in recitation that the reason for this oscillation was because of these 2 storage elements. Each of these storage elements tries to hold on to its state variable. So for example, the capacitor tries to maintain its voltage, while the inductor tries to maintain its current. And much like a pendulum, which oscillates back and forth, swaps energy between its potential energy versus kinetic energy down here, and swings back and forth. In the same way, in an LC circuit like this, energy swaps back and forth between a potential energy and a kinetic energy equivalent, which is swaps back and forth between energy stored in the inductor and energy stored in the capacitor, and sloshes back and forth. And because of this resistor, the energy eventually dissipates, and you end up getting a final value which corresponds to the 5 volts appearing here. And why is that? That's because, remember, the capacitor is a long-term open for DC. So it's a DC voltage. So after a long time, this capacitor looks like an open circuit. And the inductor looks like a complete short circuit, an ideal inductor, as a complete short circuit for DC. And so therefore, in the long term, it is as if this guy is a short, this guy is an open, so 5 volts simply appears here. And this is the transient behavior when we just switch it, we just switch the first transistor off. Okay. And in the last lecture, I left off with intuitive analysis, and let me quickly cover that and redo the intuitive analysis for you. And I left it the last time by having you think about whether the transient response would begin by going down or begin by going up. Okay? And I'll cover that today. So this was the circuit that we had, that we analyzed, a VI input with a step and an RLC out here, and we were plotting the capacitor voltage. And intuitively, we can plot this in the following way. I've also marked for you the section number in the course notes, which has a discussion of this intuitive analysis. So let's do the easy stuff first. Notice that the capacitor wants to hold its voltage. And so given that we don't have any infinite impulse here, I'm going to start out with the capacitor voltage being where it is. And the initial conditions are given to you. You are given that the capacitor voltage starts out being positive at V0, and the current starts out being negative at time 0. Okay, so I'm telling you that there is a voltage V across the capacitor at time t equal to 0, and there is a current that is flowing. Since I is negative, there's a current initially that's flowing in the opposite direction to this arrow here. Okay, the I0 is negative. So in light of that, I can start plotting my curve here by intuition. So I start by saying, okay, at time t equal to 0, I'm told that the initial voltage of the capacitor is at 0. Okay, this is about as simple as it gets, completely intuitive. I also know that after a long time, can someone tell me after a long time what the voltage will be at the end of at the capacitor? You should be able to get this by observation. VI. And why is it VI? It's VI because this is a DC value VI, and after a long time, this guy behaves like an open circuit to DC. This guy behaves like a short circuit to DC. Okay, so since it's an open circuit, VI will appear here after a long time. Okay, and so therefore, after a long time, the capacitor voltage is going to be at VI. Okay, and I just show you that. There you go. You already have the two endpoints of your curve completely by observation, intuition. Okay, no DEs, no nothing. Okay, just by staring at it and understanding the fundamentals of how simple primitive circuit elements work. Okay, absolutely simple stuff. Okay, so you've nailed the two ends now, and you can't go wrong with the stuff in the middle. Okay, so let's see. So as a next step, what I do is I need to understand, what the dynamics of the circuit looks like here. So what I do is I develop the characteristic equation, and initially you'll write the differential equation and substitute e to the st and get this characteristic equation. All right, but you can also remember it as a pattern. For a series RLC circuit, you always get an equation of this form, always. Okay, if this is R, L, and C, and whether C is, whether you're looking at L up here or C up here and L up here, as long as you're looking at the capacitor voltage, the capacitor voltage is going to behave the same. Okay, and for this circuit, the characteristic equation remains the same as well for a series RLC. It's exactly this. And I write the standard canonic form as S squared plus 2 alpha S plus omega naught squared. And omega naught is simply 1 by square root of LC. And alpha is simply R divided by L. And I have 2 in the denominator as well. And then I get omega D, which is my damped frequency, given by omega naught squared minus alpha squared. And Q is simply, it's called the quality factor. And we'll learn about Q in a lot more detail about a couple of lectures from today. That is given by omega naught divided by 2 alpha. And Q, so these parameters, alpha, omega naught, Q, and omega D, pretty much characterize everything else that I need to know about the circuit. Okay? So first of all, omega D is the frequency, okay, frequency of oscillation. Okay? And so since omega D is the frequency of oscillation, then I know that the time period of oscillation is 2 pi by omega D. Omega is in radians. Notice that for typical values of circuits like this, when R is pretty small, alpha squared is going to be very small. And in many, it's a common case for underdamped circuit that omega D will more or less be equal to omega naught. Okay, commonly that's going to be the case. So this frequency is governed by LC, and if R is large, it's governed by this value, omega D here. So I have the frequency of oscillation. I also know that Q is related to the frequency of oscillation divided by alpha. It's a ratio of the frequency divided by how badly I'm being damped. So it's a fight between the frequency of oscillation and how heavily I damp. And the ratio of that is an indication of how many cycles I ring. Okay, so Q tells me that the ringing stops approximately after Q cycles. Okay, so these four values, omega d, Q, alpha, and omega naught, are telling me more and more now. Okay, so I've got these two factors. Okay, so I know now, based on omega d and Q, that it's going to look something like this. Some, swinging, ringing here, and then I stop at this point. The last thing that's left to do here for me for now is to figure out whether I start out going down or I start out going up. Okay, so I start out going down or I start out going up. I don't know that yet. Okay, and I start at this point in the last lecture, and I let you think about how you can stare at the circuit, okay, and intuitively figure out whether this goes down or that goes up. Okay, so here's the insight. So let's stare at this for a minute, purely through intuition. The capacitor has a voltage V across it, all right? And that's because I'm telling you that it has an initial voltage V. Now, I want to find out at time t equals 0 plus, in which direction does the capacitor voltage go, increase or decrease? Okay, so what do I do? Let me take a look at the inductor current. I'm told that the inductor current is negative, which means I'm told that the inductor current is going in this direction initially. Okay, the inductor current is pushing in this direction. Now remember, just as the capacitor is one stubborn nut trying to hold its voltage, the inductor is as stubborn. It's trying to hold its current. Okay, so it's trying to maintain its current, and its initial current I0 is in this direction. So the capacitor has a voltage, okay, here, that's V0, and the inductor is yanking the current in that direction. Okay, so what happens to the capacitor? What should happen to the capacitor voltage initially? If I'm at V0, and someone is yanking current out, at least initially in that direction, what should the initial dynamics of the capacitor voltage look like? Pardon? It should drop. Okay, which means that if the initial current is being pulled in that direction, the capacitor voltage must droop to begin with. Okay, completely through intuition. Okay, no math here. So this means that I0 is negative. I0 is negative. So it's as if I0 is being pulled out in this manner. So the capacitor voltage must drop to begin life. Okay, and therefore the dynamics look somewhat like this. Okay, and notice that this is very reminiscent of the ringing that we saw at the output node of at the input node of the second, at the gate node of the second inverter. Okay. So let's stop here in terms of time domain analysis of RLC. And today, let's take another big step forward. Okay, so today marks another transition in life here. Okay, this is actually a huge transition, so I want to, just pause and, take 10 seconds of a breather, just to clearly demarcate the fact that we have a huge transition coming up. Okay? So the key to this transition is that I want to look at today the steady state response of networks to a sinusoidal drive. Okay, so we're going to do two things differently starting today in this new journey of ours. So in the past, we looked at time domain behavior of circuits. So for RLC, for example, we looked at the transient response. I mean, what happened the instant I turned something on? It was a transient response. Today, we're going to look at a steady state response. Steady state response says that if I wait long enough, okay, for whatever the circuit wants to do in the beginning of life to die out, if I wait long enough, how is the circuit going to behave after a long time? I'll tell you why that's important in a second. So I'll look at the steady state behavior. And second, I'm going to look today at sinusoidal drive. Okay, two things that are different from, say, for example, what I covered in the past 10 minutes. In the past 10 minutes, I covered two things which were different. One is that I looked at the transient response, and then steady state. And remember, for a DC input, for a DC voltage, the steady state was a DC voltage across the capacitor, correct? Okay, so the steady state was pretty boring. It was a steady state DC. But what we're going to do today is, instead of having DC inputs or step inputs, which settle to a DC value after some time, we're going to drive a circuit with a sinusoidal input. Okay, so you may ask me, Agarwal, are you nuts? Why do you want to drive something with a sinusoidal input? Why not just steps and DC and so on? Then that was painful enough. Why sinusoidal? Why not do triangular? Or why not do, some other exponentially decaying stuff, or something really cool like a wacko music signal? Why? What's special about sinusoidal stuff? Okay, and the key thing to realize is that, let me ask you a question first. How many people here know about Fourier series? Good. So it looks like some of you have taken the prerequisites. Good. So did I say more as to why this is important? Just that question should give you the answer, right? So it turns out that, so you've learned about Fourier series, and when you learned about Fourier series, you were wondering, why on earth are we learning about Fourier series? Who cares that you can represent the periodic signals as a summation of a series of sine waves? Why is it interesting? Why are you telling me that I can take a square wave and represent that as a summation of periodic square waves and represent that as a summation of sines? Who cares that I can take a sequence of pulses with a fixed period and represent that as a sum of sines? Who cares that I can take a triangular wave and represent that as a sum of sines? And I'm not sure what answer your math professors gave you when they taught you Fourier series, but in math, they're purists. They don't care about applications. The answer could well have been, because it's aesthetically pleasing. It's not, isn't it cool that you can represent a sequence of pulses as sum of sines? That's good enough for mathematicians. But I'm an engineer. If it doesn't help humanity, if I cannot see how it helps humanity in the short term, then I probably don't care too much about it. Okay, so let me give you some practical significance of this. So it turns out that since we know that we can represent periodic signals with sums of sines, what this means is that if I can figure out the behavior of networks to a sinusoidal input, okay, if I can understand how to analyze a network for a sinusoidal input, that means that if the circuit is linear, I can then compute the response of the circuit to any periodic waveform, correct? So here's the argument. I can represent any periodic waveform as a sum of sines. A Fourier series, remember. So if I just figure out how to measure figure out the response of my network for a sine wave, then if this is a linear network, I can compute the response to any sequence of scaled sum of sines. Okay, if it's a linear network, A some sine, B sine 2, omega whatever, C sine, something or the other. I can simply take the response of the one sine, and from there, I can go ahead and, knowing the response of a sine wave, I can compute the response to a sum of sines. Okay, that is pretty cool. Okay, so therefore, doing it for sinusoidal drives is really important. Well, why steady state now? Okay, hopefully I've convinced you that looking at the response of circuits to sinusoidal drive is important and interesting, because you can go to you can go long ways from there. What about steady state? Well, it turns out that, I'm going to show you, when you listen to music, so you have an amplifier, listen to music. Okay, what you're observing by and large is the steady state behavior of the amplifier. Okay, you're listening to something over many seconds or many hours. Okay, and the transients used for most of our common circuits, the transients die out very quickly. Okay, and so the transients are quite complicated, and they die out quickly. So we say, we're engineers, let's focus on what's practically important. And we'll focus on the steady state behavior as a large part of our analysis. And just completely ignore the transient response when we care about the drive to sinusoidal, or the response to sinusoidal input. Okay, the transient response is going to die away, and I'll show that mathematically to you in a few seconds. And let's focus on the steady state, because that's what I'm going to hear most of the time. I'm going to listen to an average over a long period of time. Okay? So that's the motivation behind this. And let me put this in perspective for you. And so by now, this should bring memories to your mind. This is the playground that we are in. Okay, this is the lump circuit playground here. Like remember, we came from the playground of nature to the playground of ECS, where we make the big leap from Maxwell's equations to lump circuits. That's lump circuit abstraction. And within there, we spent a large part of the last couple of months doing linear circuits. We also analyzed nonlinear circuits. You know, remember the amplifier circuit with the MOSFET, large signal analysis, was nonlinear. But we did linear and nonlinear. Within linear, we also showed that if you take a digital circuit, at least as we understood them, and draw the sub-circuit for a given set of switch settings. Okay, if I set the switches in a given way, what I was left with was another linear circuit for a given value of all the switch settings. My small signal analysis was also linear. If I focused on small signals, I also had linear analysis. So today what we're going to do is this. We're going to articulate a different part of the playground. Okay, this was a big linear playground. We've done this, we've done this. We're going to explore this territory. This is that territory of the playground in which we have sinusoidal inputs to circuits. Furthermore, we're going to look at a sub-circuit of that region, which is steady state. We'll look at sinusoidal input and in the steady state. Okay, so that's going to be our focus for the next 2 or 3 lectures. Okay, just to give you perspective of where we are. Okay, so to motivate this, what I'd like to do is consider your amplifier. This is our friend, the amplifier circuit, this part here. And remember, even though this is an amplifier, I'm using a MOSFET here. And the MOSFET, as you know, has this gate capacitance EGS. I'm explicitly drawing it out for you here. And I'm going to drive this with a bias voltage plus some small signal VI, the usual template for amplifiers. And there is some Thevenin resistance attached to that source. So I'm going to model my source as a bias voltage, a small signal, plus some source resistance. Okay? And I'm going to apply a sine wave here. And I'm going to look at what this looks like. Okay? So you may think that, look, this is a linear amplifier. And so if I apply a sine wave here, I should see some response here. And that should be, it should be the same amplitude if I feed the same amplitude here over any frequency. Okay, but let's see what happens. Keep a look at, switch over to that view graph while I show you a little demonstration here. Okay. So what you see here is 3 sine waves. A yellow sine wave, which is the input here. You see a green sine wave, which is the input VC at the gate of the MOSFET. And then you see the blue, which is the output here. So for now, simply focus on the yellow and the blue. Okay, the yellow is the input, and the blue is the output. Okay, so I apply some input, and I get a output that looks more or less some linear function of this input here. It's a small signal. So what I'm going to do is I'm going to change the frequency of the input. Remember, I want to look at the response of the circuit to a sinusoid. Okay, so I'm feeding a sinusoid here. Look at the response. I'm going to change the frequency. That's a big shift that we're making in that the curves that we drew in the last lecture had to do with varying time. Now I'm going to focus on sinusoids and vary their frequency. Okay? So I'm going to change the frequency and stare at the blue curve as I increase the frequency, and just think about what you might expect. Okay, based on the knowledge you have so far, you would expect that, look, as I change the frequency, the frequency should change, but I should see the same amplitude. Okay, but take a look. Let me increase the frequency of the input, and what do you see at the output? So I'm increasing the frequency. What do you see happening there? If you don't see anything changing there, you'll need to see an optometrist. But okay, so what do we see here? So as I change the frequency, as I increase the frequency, what happened to the blue? the blue kept decreasing in amplitude. And you're saying, whoa, what's happening here? We don't have the tools to deal with this. Okay, I expected that I'll change my frequency. My frequency here should change, of course, but why is the amplitude changing? What's happening here? That is weird. Okay? And notice that this amplitude became smaller because the amplitude of the green became smaller. And remember, the green was the voltage across the capacitor. Okay, so this is your RC, and here's my input. My input has the amplitude, which I'm holding more or less constant. And notice that VC has decreased in value as I increase my frequency. Okay? Just hold that thought. So as I increase the frequency of my input, the amplitude of the output kept diminishing. In other words, the gain of the system seemed to have decreased as I increased my frequency. Okay? And today we'll look at why that is so and how we can analyze that. Okay? The other thing that is not so obvious here is there's a phase shift. So what I'm going to do is try to see if we can observe the phase shift here. Notice here, what we have been used to is for the amplifier, we get a complete inversion at the output. Okay, inversion means a phase difference of 180 degrees for a sine wave, right? So this peak should have been here. But notice that there's a shifting of the peak. So in other words, if the yellow was my input, my output should have had its minimum when the input had its maximum. Okay, but notice there's a shifting of the signal such that the output is a maximum, not quite at the point where the input is a minimum, but a little bit after that. Also weird. So not only has this little circuit here lost its gain somehow, but also it seems to have shifted the signal in phase. Okay, that is weird. Okay, and today we will look at why that is so and try to understand the frequency behavior of this little subcomponent here. Notice that VC is exactly 180 out of phase with VO. Okay, so VO is faithfully an inverted form of inverted amplified form of the input VC. Okay, however, VC itself should have been the same as VI, but it looks quite different. Okay, so let's understand why that is so. So the sub-circuit to model is the sub-circuit comprising the source resistor and the capacitor. And I'm just showing that to you here. I have a VI, a resistor, and capacitor. Okay, I'm going to understand how this behaves. And it's a first order circuit, a single capacitor. My input is a VI cosine of omega t. VI is a real number for t greater than 0. And I'm telling you that the capacitor voltage starts out being 0. Okay, and my VI is a sinusoid. It's not a step this time, it's a sinusoid. So VI is a sinusoid, and I want to figure out what VC looks like. The behavior here tells me, I'll give you the answer, the behavior here tells me that when I feed a sinusoidal input, as the frequency increases, VC should be decreasing somehow, and also be shifting in phase. Okay, and let's do the derivation for that and see what happens. Okay, so to give you some insight as to how to go about analyzing this, let me draw a little graph as to the effort level of doing this. So to determine VC of t, on the y-axis here is our effort. Okay, how hard do we have to work to solve this circuit for a sinusoidal input? Okay, and on this graph, down here is easy, and up here is pure agony, sheer agony up here. Okay, so it's a scale of effort level ranging from easy to complete agony. And this is the time axis, and the time axis has starts out at 11 o'clock, the early part of today's lecture, and ends at roughly 12. That's today's lecture, and this is next lecture. Okay, so what I'm going to show you today is a method that uses a usual differential equation approach. Okay, and this is going to be pure agony. Okay, if you thought last Thursday was agony, watch today. Okay, this is going to be sheer hell. Okay, so I'm going to grunge through that. And I think I'll sort of give up halfway because, it's just too painful even for me here. Then what I'm going to do is at the end of this lecture, I'm going to show you an approach that I, give a cutesy name. I call it the sneaky approach. Okay, if you're going to sneak something in there, that's going to be a lot easier. Okay, and then in the next lecture, I'm going to show you an even sneakier approach that's going to just be absolute bliss. Okay, so let's start here. All right. So indulge me as I go through the agony part. Okay, I'm going to blast through it because that's not how we're going to do things. But you just need to know that that's agony. All right. So let's do a usual differential equation approach. Okay, steps 1, 2, 3, 4. Set up differential equation. Find the particular solution. Find the homogeneous solution. Add up the two. Solve for the unknowns. Okay, it's a mantra. The 4-step mantra. All right. Okay, so let's do it. Step 1, write the DE. That's easy. We've done this before for the RC circuit. It's RC dVC dt plus VC equals VI. This is no different from what you got for your RC circuit with a step input. Just that my input is VI cosine of omega t in this case. It's not just a DC voltage VI. Stare at that. Enjoy it while the going is easy. Okay? Just, it's like, traversing rapids, and before you come to a class 5, you kind of, you have a calm in the raging waters there. You kind of sit there saying, the scenery around here looks really good and so on. All you're doing is, stalling before you have to dive down to class 5. So we'll get to class 5 rapids in a few seconds here. So just enjoy this. Okay, RC dVC dt plus VC equals VI. Okay, you've seen this before. Nothing fancy. Good old stuff. VI cosine of omega t. You want to hold on to your seatbelts? Okay. Okay, so let's find a particular solution to the cosine input. Okay, so let's use our standard method. And what I'll do is just so there's going to be so much crapola up there that I draw your attention to VP, which is what we're trying to get. I'm just going to put a box around VP in red. Okay, if you see like all sorts of garbage up here, just look for the red square. Okay, that's what we're trying to get at. Okay, that's the equation. Okay, so let's try. First try. Gee, A worked before, a constant value A worked before for DC inputs. Let's try that again. If it worked then, it may work now. So if I use A, a constant value, and I substitute it here, I get dA dt goes to 0. VP is A, but on the right-hand side I have VI cosine omega d. Okay, so clearly A doesn't work. Sorry, I struck out. Well, aha! Cosine omega t here, let's try A cosine omega t as my particular solution. Okay, things are getting a little harder now, a little more painful. So substitute A cosine omega t here. So I do get A cosine omega t for VP, but out here I get RC A sine omega t times omega times -1. So I have a sine and a cosine, and then I have a cosine on the right-hand side. Sorry, doesn't work. Nope, doesn't work either. Well, let's try A cosine omega t plus phi. Okay, so we're now embarking into the rapids here. Okay, you can begin feeling the pressure. So, just to refresh your memories of sines and cosines, A is the amplitude of the cosine, omega is the frequency, and phi is the shape, the phase. Remember the signal I showed you earlier. Something happened to the amplitude of the sine, something happened to the phase. So A cosine omega t plus phi. Okay, let me plug it in here and go by standard practice. So here's what I get. So I plug in A cosine omega t into this equation, and this is what I get. Okay, I differentiate it, so I get omega out minus sine omega t plus phi. A cosine omega t plus phi equals VI cosine omega. That might work. That might work. So let's now we get into the class 6 part of the class 5. All class 5s are a little bit of class 6 rapid. So remember, and the rapids go on an exponential scale, so it's like earthquakes. So what I do now is that I expand out sine omega t plus phi, Sine omega t plus phi, sine omega t plus cos phi minus, blah, blah, blah. It just goes on and on. I could go on and on, but, this is even tiring me here. So this can be made to work. Okay, but I'm not sure I want to put all of us through this trig nightmare here. Okay, if I'm really, really nasty, I can give this to you as a homework assignment or something. Okay, but I'm not that nasty, so you won't see that. Okay, but if I go down this path, it'll get me to the answer, but I would have to soon negotiate class 6, class 7 rapids to get to where I want. So let me punt on it. Okay, let me start from scratch. Okay, so I'm at step 2. Let me start from scratch. Okay, instead what I'd like to do is let's get sneaky here. So rather than negotiating the class 5 rapids, what we can say is, aha, we can take our canoes and jump onto shore and run down and then get back onto the river. Let's do that. That's called the sneaky approach, so that all our friends who are behind us think to negotiate the rapids, but what we're going to do is get sneaky, take the shore path. So let's get sneaky here and just walk down the shore and see what's there, okay? So I'm going to do something completely weirdo here. I'm going to look at solving this equation through the shore method. Okay, S stands for shore, or S stands for sneaky, whatever you want. Okay, so what I'm going to do is, rather than try to solve for VI cosine omega t, I'm going to say, let's try a different input altogether. Okay, and you'll understand why in a second. It's like I'm the captain of my canoe, and I tell my teammates, hey, let's not negotiate the rapids. Let's go and explore the shore. Maybe down the shore we can find a path that gets us across to the other side more easily. Okay, so here's me and my colleagues, carrying our canoe and getting onto shore and taking a sneaky path. So this is not what I set out to solve. Okay, but I don't know where this will lead me, but let's see where the shore path leads us. Okay, so I'm going to try solving this equation, VI e to the st. Okay, S stands for shore or sneaky, whatever you want, right? So I don't know where I'm going, but let's see where this leads us. Let's explore, okay? Make believe you're Columbus or something. Okay. So I don't know, let's use the usual techniques and see how this works out. So let's try a particular solution, Vp e to the st. So my input is Vi e to the st. I'm trying to solve the circuit for a different input. And let me try a solution Vp e to the st and see if that works out nicely. So I substitute Vp e to the st into my equation here. So Rc Vp e to the st, blah, 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 blah. Okay, so what I get here is Vi st. Vp st stays the same, but here Vp comes out, S comes out, and e to the st stays the same. So that's a nice property of exponentials, and this is what I get. A really cool property of exponentials is that when I differentiate it, I get the exponential back. Unlike a cosine, I got a sine, and for a sine, I got a cosine. Exponentials are, very plain and simple, are straightforward. Okay, what you see is what you get. You differentiate it, you get the same thing. You get some other, some scaling, Vp and S and so on, some scaling here. You get an S scaling here, but the basic form stays the same. This is quite nice. Okay, so I've e to the st in all 3 places, so I can cancel those out, and I get this expression, and I get this. Wow! So if I go down the shore, I get someplace fast. I don't know where I am yet, but whatever I did, it was easy. Okay, I'm just exploring this path, down the shore path. I'm making progress. I don't know where I've gotten yet. We'll see where we got to in a second, but I got someplace quickly, fast. Okay, I was able to solve for this input, Vi e to the st, and get the solution very quickly. So what happened here? So I assumed a solution of the form Vp e to the st, substituted it back, and found that if Vp were equal to Vi 1 plus SRC, then Vp e to the st is a solution. So what I've done here is that Vi divided by 1 plus SRC is a solution, a particular solution to this equation for the input Vi e to the st. Okay, I put a box around it because this is important. This was easy. So we went on to shore and said, let's try this other input. And we made rapid progress on shore. And I got someplace. I don't know where I am yet. I got this. Okay, let me pause here, and let me give you the final answer. I'm going to show you over the next 5 minutes that this is our answer. You're staring at the answer already. Okay, so I and my party have taken the shore path, and we've gotten someplace, and we see the river there. Okay, it turns out we're exactly where we want to be, just after the rapids. So all I have to do now is get my colleagues into the river with myself in the canoe, and we're done. Okay, you don't know that yet. So my colleagues and I are sitting on the shore, looking at the river. So we've got someplace. There's no rapids there. We've got someplace. We don't quite know, is this just after the rapids or not? We don't know yet. Okay, but I got there very quickly. And I'll tell you right now that that is the place we wanted to go to. And the next 5 view graphs I'm going to blast through, there's going to be more pain and agony to show you why that is the case. Okay, it's me thinking I'm Columbus and proving to my colleagues that this is where we want to be. Okay, and pulling out my sextant and all my the compasses and so on that cartographers and people use, and to prove to my colleagues that this is where I want to be. Okay, this is the answer. Okay, next 5 view graphs will be demonstrating that this is indeed the answer, or close enough to the answer that we'll be satisfied. Okay, so isn't this spectacular? I'm going to show you in about 5 minutes that this gives us all the information we need to know to compute the sinusoidal steady-state response to this differential equation. Okay, and we will come. Let me write that down here, just so you know. Just so you remember, I'm going to put a marker on the shore that says this is where we are right now. Okay, now let me prove to you. Okay. So as I just said, VPS is VI, it's this stuff here, multiplied by e to the st, is a solution for VI e to the st. Okay? So this guy here is a solution for VI e to the st. And VP is simply the coefficient that multiplies e to the st. Similarly, if I substitute S equals j omega, okay, I told you 5 view graphs of more hell, but I'm just going to prove to you that this is it. So I'm substituting S equals j omega. Okay, now this is Columbus giving a big speech at the end, convincing his colleagues that we are where we want to be. Okay, so S equals j omega. So I substitute j omega for S, and this is what I get. Okay, so this is a solution for e to the st. And so this is the solution for e to the j omega t. Okay? And let me mark this for you as something to remember. Okay, VI divided by 1 plus j omega RC. So in terms of that, okay, I'm substituting j omega for S, and this is a complex number. It's a complex amplitude. It's a complex number because of the j here, and it multiplies e to the j omega t. Just keep this in mind. Okay, so that was easy. Okay, the steps were easy. I'm still proving to you that this is where we want to be. Okay, so now let me draw the connection back to VP. And the first fact was that finding the response to VI e to the j omega t was easy. We know that. Second was that is the following observation, that VI cosine omega t, okay, simply the real part of this number here. So VI cosine omega t is simply the real part of VI e to the j omega t. Okay, from the Euler relation. So cosine omega t is simply the real part of this guy. Okay? So a light bulb's beginning to go off. So the first fact was that finding the response to VI e to the j omega t was easy. And the response was this, right? Times e to the j omega t. That was easy. All right? And the second part is that the real part of this is VI cosine omega t was our input. So to draw the connection between 2 steps, finding the response to VI e to the j omega t was easy. The real part of that was the input we cared about. Okay, our light bulb's going off. So let me draw you a little picture here to show you what's happening. So response to VI is VP. It's a particular response we're looking for. Remember the red square. But we threw in a sneaky input, VIS, and we found the response VPS to that. Okay, this step was easy. This step was hard. VI to VP was hard. Trig nightmare, remember? But VIS to VPS was easy. It was a simple, VP e to the j omega t, VP e to the st thing. And we also know that the real part of VIS is VI. The real part of this is simply VI. So if we have a real circuit, if we have a real linear circuit, okay, for a linear circuit, if the real part of this gives me VI, then the real part of the solution should give me VP. So computing VPS was easy. So if I take the real part of this, I take the corresponding real part of this. Okay? So this is sort of an inverse superposition argument. For superposition, I said, take the response for A, take the response for B, add them up, you get the response for A plus B. Here what we're saying is that get the response to A plus B, all right, or to A plus JB, and the real part of the input will produce a response given by the real part of the output. Okay, so this is an inverse superposition argument. So it's a linear circuit, then if VI is a real part of this sneaky input, then I find the response to the sneaky input and take its real part, I should get VP. So here I am, Columbus, standing down at the entrance to this part of the river. I just proved to my colleagues that all we have to do is take the real part of what we have. Okay, we can just jump right back into the river and get back to VP. Okay, and what I'm going to do next is just grind through the math and show you that. I'll just blast through it. It's not important, but you have it in your notes. So I'm telling you that VP is simply the real part of the sneaky output, and I take the real part of VP e to the j omega t, and I take the real part, and let me just a bunch of math here. Okay, so I'm just taking the real part and doing a bunch of complex math. So remember, VP was given by this quantity here, and I take the real part, and I end up with VP is simply this quantity multiplied by cosine omega t plus phi, where phi is given by tan inverse of omega RC. And this is the coefficient multiplying the cosine. Okay, so by taking the sneaky path and then taking the real part of that output answer, I was able to very quickly get to where I wanted to be. Okay, so from here to here, it's only math. And recall that VP, the thing in the red, was what we set out to find out, which is a particular response to VI cosine of omega t. Okay, and remember that 2 grunge is all of this stuff. So I'm going to blast through 2 or 3 more view graphs that just give you more insight and more math, nothing particular. And remember, to solve the equation, we have to find a homogeneous solution too. But recall that the homogeneous solution for our RC circuit is of the form A e to the minus t by RC. Okay? This means that as time becomes very large, this part goes to 0. Right? As time becomes large in the steady state, remember I care about the steady state. This goes to 0. And so I don't care about the homogeneous solution. Isn't that fantastic? For most of the circuits we will deal with, except for purely oscillatory ones, the homogeneous part dies away. You have something like e to the minus t or whatever. It just dies away. It's gone. Okay? So the total solution has VH going away. And what I end up with is just VP. So my total solution in the steady state is simply VP. And A is given by this that we just calculated. Okay? So I just have a bunch more insight that I talk about that we can look through in your notes. And I just want to show you a very quick summary. So in summary, what we have is we computed VP. It was a complex coefficient. And all these steps, 2, grunge, 3, and 4, were a waste of time. And what I showed you was that for the input VI, the coefficient VP was complex. And I can take the ratio and represent it in this manner as well. Okay? And from VP, I can then compute the multiplier for the cosine as follows. I divide by VP here. Remember, the cosine was multiplied by, in the mathematical step that I did, VI divided by 1 plus this stuff here. So I can get the magnitude and phase of the transfer function of the circuit in the following manner. And to wrap up very quickly, I'm going to cover this again the next time and show you a magnitude plot. And notice here that if I plot VP divided by VI, remember this was VP here. That's the answer. Okay? The magnitude looks like this. On a log scale, VP over VI, for small frequencies omega, it's at 1. But as omega increases, VP over VI keeps decreasing. Okay, that is the output. Remember, mod VP was the amplitude of the output. That keeps decreasing. And this is the reason why, as I increase the frequency, the amplitude of my output cosine kept decreasing. I can also plot the phase for you. And the phase, in the same manner, as omega increased, my phase also kept shifting from 0 initially to pi by 2 finally. Okay? Let me stop here and start with this the next time and revisit this. Unfortunately, I won't have time for the demo. I'll show it to you next time.